Welcome to DAR Tutors. Today, we will begin our study of vectors, a fundamental concept in IB mathematics, applications and interpretation at the higher level. By the end of this video, you will be able to distinguish between scalars and vectors, represent vectors geometrically, perform basic vector operations like addition, subtraction, and scalar multiplication, and express and manipulate vectors in two dimensions using their components. First, let's establish the key difference between two types of quantities we use in mathematics and physics: scalars and vectors. A scalar is a quantity that has only magnitude or size. It does not have a direction. Think about quantities like mass, distance, speed, and time. For instance, you could say an object has a mass of 5 kilograms, a distance of 10 meters, or a speed of 60 kilometers per hour. These descriptions are complete without mentioning direction. In contrast, a vector is a quantity that has both magnitude and direction. It's not enough to say something is happening, you must also say in what direction. Examples of vectors include displacement, velocity, acceleration, and force. A common way to illustrate this distinction is with speed versus velocity. Speed, like 60 kilometers per hour, is a scalar. Velocity is a vector, so it includes both the speed and the direction, for example, 60 kilometers per hour to the north. A useful way to visualize a vector is with a directed line segment, or simply an arrow. In this representation, the length of the arrow signifies the magnitude of the vector, and the arrowhead points in the direction of the vector. For example, a longer arrow would represent a greater force, and an arrow pointing right would indicate a force to the east. Let's work through an example to see how this is done. Our objective here is to learn how to represent vector quantities geometrically. We're asked to draw a scale diagram representing a force of 30 newtons in a northeasterly direction. A northeasterly direction means it lies exactly between north and east. First, we must define a scale. The problem states we can use a scale where 1 centimeter represents 10 newtons. This scale helps us convert the vector's magnitude into a measurable length. So, to represent a force of 30 newtons, we'll need an arrow that is 3 centimeters long. This length, 3 centimeters, directly corresponds to the vector's magnitude. Next, we need the direction. Northeasterly is 45 degrees from the east axis. So we'll start at an origin, draw a 3 centimeter line, and ensure its direction is 45 degrees relative to the east direction. We can use a compass to get this right. Here we see the final diagram. A line of 3 centimeters pointing 45 degrees up from the east axis. This single arrow visually represents the vector quantity. So we've now seen that a vector, with its magnitude and direction, can be effectively represented by an arrow whose length corresponds to the magnitude and direction corresponds to the arrow's orientation. Now that we know how to represent vectors visually, let's explore the standard notation used in mathematics to define them. Our objective here is to understand and use formal vector notation. In this notation, vectors are often represented by letters, either bolded or with an arrow on top. A vector is defined by its origin, which is the point where the arrow begins, and its termination, or head, which is the point where the arrow ends. We have two primary ways to denote vectors. A vector can be labeled with a single lowercase letter, like A, often in bold to distinguish it from a scalar. We can also define a vector using its start and end points. For instance, a vector from point A to point B is written as vector AB. This second method, using start and end points, is particularly useful when we're defining the vector in relation to other points. Let's formalize this. A vector can be the vector from point A to point B. Its origin is A and its termination is B. The symbol used is vector AB. The magnitude of a vector, which is just its length, is denoted using vertical bars. So, the magnitude of vector AB is written as the absolute value of AB. This signifies the length of the arrow. A special case is the position vector. When a vector's origin is the origin of a coordinate system, typically denoted as O, and its termination is a point P, it's called the position vector of P. So, the vector from O to P is the position vector of P. It's written as vector OP, and its magnitude is the distance from the origin to point P. An essential concept in vector notation is that a vector's definition depends only on its magnitude and direction. It does not depend on its starting position. This is why we say vectors are free. This means we can move a vector around in space as long as its length and direction remain unchanged, and it will still be considered the same vector. So, to recap, we've established two key ideas: that a vector can be identified by a single bold letter or by its start and end points, and that a vector is a free object, meaning its position does not affect its identity, only its magnitude and direction matter. Let's expand on the geometric properties of vectors. In this scene, we will define what it means for vectors to be equal and explore the concept of a negative vector. Two vectors are considered equal if and only if they possess both the same magnitude and the same direction. It's crucial to have both conditions met. If their lengths are different, they are not equal. If their directions are different, even with the same length, they are not equal. This means equal vectors must be parallel, point in the same direction along their parallel lines, and be of the same length. Visually, they are simply translations of one another. The concept of free vectors we just discussed fits perfectly here. Any arrow that is parallel, in the same direction, and of the same length as a given vector A is also vector A. The position doesn't change what the vector is. Next, let's consider the negative of a vector. The negative of a vector A, denoted as negative A, is the vector that has the exact same magnitude as A, but points in the completely opposite direction. This is like an arrow pointing to the east and its negative pointing to the west with the same length. Or an arrow from point A to point B, vector AB. The vector BA from B to A is its negative. They are collinear, but their arrowheads oppose each other. In formal notation, the negative of vector AB is vector BA. So we can write the relationship. Vector BA equals negative vector AB. Let's use an example to solidify these geometric concepts. We have a parallelogram PQRS with vector PQ defined as A and vector QR defined as B. We need to find expressions for the other vectors in terms of A and B. Recall that in a parallelogram, opposite sides are parallel and equal in length. First, find vector QP. This vector goes from Q to P, which is the opposite direction of vector PQ. Since PQ is A, vector QP is its negative, negative A. Next is vector RQ. This is the opposite direction of vector QR. So vector RQ is negative B. For vector SR, we look for a vector that's parallel and in the same direction. In a parallelogram, vector SR is parallel to and in the same direction as vector PQ. Since PQ is A, vector SR is also A. Finally, for vector SP, it's parallel to and the same length as vector QR, but in the opposite direction. Since QR is B, vector SP must be negative B. This example beautifully demonstrates how the properties of parallel lines and opposite directions define equality and negative vectors in geometric figures. We've successfully used our definitions of vector equality and negative vectors to express all sides of the parallelogram. We've focused on representing individual vectors. Now let's explore how to combine them. A major objective of this scene is to learn how to add vectors geometrically. Geometric vector addition, also known as the triangle rule, provides a way to combine vectors visually. Think of it as following a path. Imagine you walk from town P to town Q, and then from town Q to town R. Your final position is at R. The single direct trip from P to R is the geometric sum of your two walking trips. In vector notation, this is written as vector PQ plus vector QR equals vector PR. Notice the pattern. The head of the first vector, Q, matches the tail of the second vector. The resultant vector then spans from the first tail to the last head. This gives us a general rule for adding any two vectors, say A and B. Step 1. Draw the first vector A. Step 2. Draw the second vector B so its tail is at the head of vector A. Step 3. Draw a new vector from the tail of A to the head of B. This new vector is their sum, A plus B. Let's apply this rule to a specific example. We're given two vectors, A and B, on a grid, and we need to construct A plus B geometrically. First, we draw our starting vector, A. Now we take vector B. Remember, vectors are free, and move it so that its starting point coincides with the end point of vector A. We must make sure to preserve its direction and length perfectly. Once B is positioned correctly, the resultant vector, A plus B, is the arrow that goes directly from the very beginning of A to the very end of B. The result is a vector starting at the tail of A and ending at the head of B. This new arrow is the vector sum, A plus B. We've successfully used the triangle rule to combine the two vectors into a single resultant vector. We can extend this idea to multiple vectors. If we have a sequence of vectors that connect tail to head, their sum is simply the vector that closes the figure, running from the tail of the first to the head of the last. For example, vector AB plus vector BC plus vector CD equals vector AD. This method simplifies complex paths into a single direct displacement. We have now seen that by following vectors tail to head, we can find their geometric sum, which represents the overall journey. There are two special vectors that are important to understand. In this scene, our objectives are to define the zero vector and geometric vector subtraction. The first is the zero vector, which is written as a bolded 0. As its name implies, the zero vector has a magnitude or length of 0. It represents a state of no displacement or no force. A key question arises. Does the zero vector have a direction? Given it has no length, it doesn't point anywhere. Therefore, the zero vector is unique in that it is the only vector that does not have a defined direction. It behaves like the number 0 in arithmetic. For any vector A, adding the zero vector does not change the vector A. And crucially, the sum of a vector and its negative is the zero vector. A displacement A, followed by an equal displacement in the opposite direction, negative A, returns you to your starting point, resulting in a net displacement of 0. This identity leads us directly to the concept of vector subtraction. To subtract vector B from vector A, we simply add the negative of B. So, the operation a minus B is equivalent to a plus negative B. Visually, we draw vector A, and then from its head, we draw vector B pointing in the opposite direction. The resultant vector goes from the tail of A to the head of negative B. Now, let's use these ideas to simplify some vector expressions. Our objective is to apply these definitions in problem solving. We'll work with the points A, B, C, D, and E shown in the diagram. First, let's simplify vector BC plus vector CA. Using the triangle rule, the head of BC is C, which is also the tail of CA. Therefore, their sum is the vector that goes directly from B to A. Next up, vector BA plus vector AE plus vector EC. Again, applying the triangle rule, we can simplify this step by step. BA plus AE becomes BE. Then, BE plus EC becomes BC. This demonstrates the power of the triangle rule for any number of consecutive vectors. One more to show the zero vector, vector AB plus vector BC plus vector C. The sum of the first two, AB and BC, is AC. Then we add CA, but CA is the negative of AC. So the sum is AC minus AC, which equals the zero vector. Graphically, we traveled from A to B, then B to C, then C back to A, resulting in no net change. We have now defined the zero vector as a vector of zero magnitude with no direction, and we've established that vector subtraction is equivalent to adding the negative vector. These concepts are foundational for all further vector algebra. So far, we've added and subtracted vectors. Another crucial operation is scalar multiplication. Our objective here is to understand how multiplying a vector by a scalar changes its magnitude and direction. Recall that a scalar is a quantity with only magnitude. When we multiply a vector by a scalar, we perform scalar multiplication. The result is always another vector. The effect of scalar multiplication is straightforward. The magnitude of the original vector is scaled by the scalar, and its direction is either preserved or reversed depending on the sign of the scalar. For a positive scalar k, multiplying a vector a by k creates a new vector, k, that is k times longer than a but points in the exact same direction. For instance, if 3a is 3 times as long as a and points in the same direction. For a negative scalar k, multiplying a by k scales the magnitude by the absolute value of k, but it reverses the direction. So, 3a is 3 times as long as a, but points in the opposite direction. A key takeaway is that scalar multiples of a vector are always parallel to the original vector, just with a different length. Now let's see this in action by constructing a linear combination of vectors. We're given vectors r and s and need to construct 2r plus s. First, we draw the vector r. Then, to get 2r, we draw another vector r from the head of the first one. We now have an arrow that is twice the length of r. Next, from the head of 2r, we draw vector s. Finally, the sum, 2r plus s, is the arrow from the tail of the first r to the head of s. Let's try another one with a negative scalar. Construct our minus 3's. This is equivalent to r plus negative 3's. So we first draw vector r. From its head, we need to add negative 3's. To do this, we first find the negative of s at s. Then we draw s 3 times in a row, tail to head. The final resultant vector goes from the tail of r to the head of the third s arrow. This shows how scalar multiplication is combined with vector addition. We can scale vectors up, scale them down, and reverse their direction before adding them together. Let's look at one more example. Sketch vectors p and q if p is equal to 3 times q. First, we would sketch a vector and label it q. Then we would draw a second vector, p, that points in the exact same direction as q, but is visually 3 times its length. This diagram clearly shows the relationship defined by the equation. What if p equals negative 1/2 q? We sketch vector q as before. Then we draw vector p pointing in the opposite direction. Furthermore, it must be only half the length of vector q. This gives us a new vector that is parallel but oriented oppositely and scaled. To summarize, we've learned that scalar multiplication scales the magnitude of a vector and can reverse its direction. This operation always results in a vector parallel to the original, which is a powerful geometric property. So far, our approach to vectors has been primarily geometric. We've used arrows to visualize their magnitude and direction. This method is intuitive, but it can be imprecise, especially when working with complicated diagrams. To overcome this limitation, we move to an algebraic approach. The objective of this scene is to introduce vectors in a plane using components, a method that brings precision and power to vector calculations. The foundation for this is the Cartesian coordinate system. When we plot a point, say P2 to 5, we move 2 units along the x-axis and 5 units along the y-axis. This suggests that any movement or displacement in a plane can be broken down into 2 independent components, a horizontal one and a vertical one. We can define 2 special vectors to help us with this. The vector I is the base unit vector in the positive x direction. It's a vector of length 1 pointing right. The vector j is the base unit vector in the positive y direction. It's a vector of length 1 pointing up. These vectors are orthogonal, meaning they are at right angles to each other. Now let's consider a point P with coordinates x, y. The position vector from the origin O to P can be thought of as a displacement of x units in the x direction and y units in the y direction. We can express the position vector OP in 2 main forms. The unit vector form is xe plus yj, which shows the displacement as a combination of our base unit vectors. Alternatively, the component form is a column matrix, x over y, where x and y are the horizontal and vertical components respectively. Both forms represent the same vector. The choice of which to use is often one of convenience or preference. The equality of vectors is much more precise in component form. Our objective is to now understand this algebraic definition of equality. Algebraic vector equality states that 2 vectors are equal if and only if their corresponding components are equal. This is a very clear and testable condition. Let's work through an example to illustrate this. We're given 2 points, A at 3 to 1 and C at 2, and we're told vector CB is equal to vector OA. Our goal is to find the coordinates of point B. First, we find the component form of vector OA. It starts at the origin O00 and goes to A, 301. The change in x is 3 minus 0, which is 3. The change in y is 1 minus 0, which is 1, so vector OA is 3 over 1. Now we write vector CB. Let's assume the coordinates of B are x, y. The components of vector CB are the x-coordinate of B minus the x-coordinate of C and the y-coordinate of B minus the y-coordinate of C. This gives us the vector expression for CB. The problem states these 2 vectors are equal. Therefore, their corresponding components must be equal. We set up 2 equations. X plus 1 equals 3 and y minus 2 equals 1. Solving the first equation, we find that x equals 2. Solving the second, we find that y equals 3. So the coordinates of point B are 2, 3. This shows how the algebraic definition of equality allows us to solve for unknowns. Let's summarize. We've introduced the component form of vectors, which provides an algebraic, precise method for working with them. We've also defined vector equality algebraically. Two vectors are equal if and only if their components match. Now that we have vectors in component form, we can define magnitude algebraically. The objective of this scene is to learn how to calculate the magnitude of a 2D vector using its components. Geometrically, the magnitude of a vector is its length. If a vector starts at the origin and ends at a point, A1, A2, it forms the hypotenuse of a right-angled triangle. The horizontal side has length A1 science, and the vertical side has length A2. We can then use the Pythagorean theorem to find the length of the hypotenuse, which is the vector's magnitude. The theorem states that the square of the hypotenuse is the sum of the squares of the other two sides. So, for a vector A with components A1 and A2, the square of its magnitude is A1 squared plus A2 squared. Taking the square root, we get the magnitude, denoted with vertical bars, is the square root of the sum of the squares of its components. A unit vector is any vector that has a length or magnitude of exactly 1 unit. We've already seen that I and j are base unit vectors. Finding a unit vector that points in the same direction as any given non-zero vector A is a common task. We call this the unit vector of A. The formula is to take the original vector A and divide it by its magnitude. This operation preserves the direction while scaling the length down to 1. Let's work through some examples. Our objective is to calculate magnitudes and work with unit vectors. Given vector p is 3 over 5, we need to find its magnitude. Using our formula, we take the square root of 3 squared plus negative 5 squared. This simplifies to the square root of 34 units. Now for an example involving unit vectors. The objective here is to find an unknown component given that a vector is a unit vector. We are given a vector with components negative 1/3 and k, and we know it's a unit vector. This means its magnitude must be 1. So we set the magnitude equal to 1. The square root of negative 1/3 squared plus k squared must equal 1. Squaring both sides gives us 1/9 plus k squared equals 1. Rearranging the equation to solve for k squared, we get k squared equals 8/9. Taking the square root, we find two possible values for k, positive or negative square root of 8 over 3. Both values will result in a vector of length, 1. We've now established a rigorous way to calculate the length of a vector using its components and defined unit vectors as vectors with a magnitude of 1. This algebraic approach removes the ambiguity of drawing and measuring. With vectors in component form, operations become incredibly straightforward. In this scene, our objective is to define vector addition, subtraction, and scalar multiplication using their components. Algebraic vector addition is a direct translation of the geometric process. When we add two vectors, we simply add their corresponding components. So if vector A is A1 over A2 and vector B is B1 over B2, their sum is a new vector whose horizontal component is A1 plus B1 and whose vertical component is A2 plus B2. It's that simple. Following from this, vector subtraction is also component-wise. To subtract vector B from vector A, we subtract their corresponding components. This is consistent with our earlier geometric definition of adding the negative vector. So the result of a minus b is a new vector with components a1 minus b1 and a2 minus b2. Finally, algebraic scalar multiplication is just as easy. To multiply a vector by a scalar k, you multiply each of its components by that scalar. So k times vector a is a new vector with components k times a1 and k times a2. This operation perfectly captures the geometric scaling and direction change we discussed earlier. Let's apply these rules in a combined example. Our objective is to perform a series of operations using these component rules. Given vectors p, q, and r, find p minus q minus r. We can perform these subtractions component-wise. The new x component will be 3 minus 1 minus negative 2, which is 4. The new y component will be -2 minus 4 minus -5, which is -1. The result is the vector 4 over -1. Now let's incorporate scalar multiplication. Given vectors p and q, find 1/2 p minus 3q. We will work with the unit vector form here. First, we substitute the expressions for p and q. Then we distribute the scalars 1/2 and -3. This gives us 2i plus 1/2 j plus -6i plus 9j. Finally, we collect the I components and j components to get our final answer. -4i plus 9 and 1/2 j. Notice how these algebraic rules make complex combinations straightforward to calculate. This seems like a good point to remind you that if you're finding these concepts challenging, or if you'd like more personalized expert guidance in IB, A-Level, or IGCSE curricula, please don't hesitate to contact DAR tutors for online and home tuition. Our experienced tutors are ready to help. In summary, we've formalized vector operations with concise algebraic rules. Add or subtract corresponding components, and multiply each component by a scalar. This algebraic framework is crucial for higher-level vector work. Let's work through one more comprehensive example, combining everything we've learned so far. Our objective is to find the magnitude of a vector that is a complex linear combination of other vectors. We are given two vectors, p and q, in unit vector form. Our task is to find the magnitude of p minus 2q. To solve this, we will follow a two-step process. First, we will calculate the vector p minus 2q algebraically. Second, we will find the magnitude of the resulting vector using our formula. Step 1. Calculate the vector p minus 2q. We start by substituting the expressions for p and q into the vector expression. This gives us 3i minus 5j minus 2 times the quantity -I minus 2j. Next, we distribute the scalar 2 to both terms inside the parentheses. -2 times -I is positive 2i, and -2 times -2j is positive 4j. The expression now reads 3i minus 5j plus 2i plus 4j. Now we group the I components and the j components. Combining the terms, 3i plus 2i equals 5i, and -5j plus 4j equals -j. So the vector p minus 2q is equal to 5i minus j. We have completed the first step. The vector we need to find the magnitude of is 5i minus j. Step 2. Find the magnitude of the resulting vector. The vector 5i minus j corresponds to the component form 5 over 1. The magnitude formula is the square root of the sum of the squares of the components. Plugging in the components, we get the square root of 5 squared plus -1 squared, which is the square root of 5 plus 1. This gives us a final magnitude of the square root of 26 units. We have successfully found the magnitude of the complex linear combination. In this scene, we've demonstrated how to combine scalar multiplication and vector addition-subtraction to simplify complex vector expressions, and then find their magnitude algebraically. This multi-step problem-solving process is typical of what you'll see in HL-level questions. Now it's time to test your understanding with some practice questions in IB style. Remember to pause the video after each question and attempt to solve it before watching the solution. Our objective here is to apply the concepts learned to solve IB-style problems. Question 1 asks for the length of the vector 4i minus 3j. To find the length or magnitude, we will use the Pythagorean theorem. Pause here and give it a try. The solution is to take the square root of the sum of the squares of the I and j components. That is, the square root of 4 squared plus -3 squared, which is the square root of 16 plus 9, or the square root of 25. The length of the vector is 5 units. Question 2 asks for the magnitude of a linear combination of vectors p and q. We will first calculate the resulting vector and then find its magnitude. Pause the video and solve this. First, we calculate the vector. 3p minus 2q is 3 times the vector, 1004 minus 2 times the vector, 2 to 1. This gives us the vector 3012 minus the vector 4.2. Subtracting component-wise, we get the vector 7 tau 10. The magnitude is the square root of 7 squared plus 10 squared, which is the square root of 149. For our third question, let's explore vector equality. Question 3 presents an equality between two vectors with unknown scalar variables a and b. We must find the values that make this equation true. Think about how we solve for unknowns in an algebraic vector equation. Let's work through the solution. First, we perform the scalar multiplication on the left side, giving us 15, 5b. Then we add the two vectors on the left, resulting in 17, a plus 5b. We equate the components, giving us 2 plus 15 equals 17, which is true, and a plus 5b equals 8. This is our key equation. Since we don't have enough information from this single question to find two variables, we recognize there are infinitely many pairs, A, B, that satisfy this. If the problem had provided another piece of information, like a second equation, we could have found unique values for A and B. Let's move on to the next question. Question 4 asks whether the vector 2, 3, 1/3 is a unit vector. To answer this, we need to calculate its magnitude. Work this one out. The magnitude is the square root of 2/3 squared plus 1/3 squared. This simplifies to the square root of 4/9 plus 1/9, which is the square root of 5/9. This value is not equal to 1. Therefore, the vector is not a unit vector. Our final question is a bit more challenging. It's about finding an unknown component p, given the magnitude of a vector. Pause and solve this problem. It requires setting up and solving a quadratic equation. Here is the solution. We set the magnitude equal to 10. This gives us the square root of p squared plus the quantity p minus 2 squared equals 10. Squaring both sides, we get p squared plus p squared minus 4p plus 4 equals 100. Combining like terms, we arrive at the quadratic equation 2p squared minus 4p minus 96 equals 0. Dividing by 2 simplifies it to p squared minus 2p minus 48 equals 0. This factors to p minus 8 times p plus 6 equals 0. Therefore, the two possible values for p are 8 and -6. Well done for working through these questions. We have now covered the foundational geometric and algebraic concepts of 2D vectors, fulfilling our initial objectives. Mastering these basics is essential for the more advanced topics in IB/AI/HL. Thank you for watching this introductory video on vectors. If you found this explanation helpful and wish to deepen your understanding, or need assistance with other areas of the IB, A-Level, or IGCSE curricula, please contact DAR Tutors. Our team of expert tutors is available for personalized online and home tuition, offering the support and guidance you need to succeed. Visit dartutors.com or contact us today to learn how we can help you achieve your academic goals. Thank you.